Hello everyone, myself Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the last class, we discussed problems on shear flow and shear center. We took one problem and we tried to solve it, and then in the present session also, we'll take some more problems, additional problems, and we'll try to solve the shear center. And for that, let's try to understand the first question that is given, that is find the position of shear center of a rectangular 4 boom beam section shown in figure. And he mentioned that the boom carries only direct stresses, but the skin is fully effective in carrying both shear and direct stress. And he has given the area of each boom as 100 mm square. So this is very important line, and that is not you get in all the questions. This is a separate point that is given. What he has given, usually we try to consider booms carry all the direct stresses while the skin is effective only in shear. Okay, but here what he mentioned here it is, he mentioned the skin is fully effective not only in shear, but he mentioned that the skin is fully effective in carrying both shear and direct stress. And when he mentioned that the skin is fully effective in carrying the bending stresses as well as the shear stresses, then you have to consider the effect of the booms, and also you have to consider the effect of the panel, that is the skin between the booms also. Okay, so usually we'll take directly the analysis of booms, but now when the skin is fully effective in carrying both shear as well as the direct stresses, so you have to consider the effect of this panel as well as the boom and the skin as well. Okay, so that is a change we have. So usually in the problem we'll write BR summation BR YR R equals to 1 to N for when you have booms. Now for this problem you have to add integral 0 to S, and even for this skin you have to write it as T into X into ds or T into Y into ds depending upon to the symmetry. Okay, so if the symmetry, if you consider, is symmetrical about horizontal axis, so therefore you have to consider this as T into Y into ds. So both you have to consider, this you need to consider as well as this you need to consider in the analysis. Okay, so let's look into this problem. And the given section is again symmetrical about horizontal axis, not about vertical axis, only horizontal axis, and it is a closed section. So the formula for shear flow QS is equals to since it is symmetrical, you can substitute Ixy equal to 0, and since it is symmetrical over horizontal axis, the shear center lies on the horizontal axis of symmetry. Vertical shear load is not given, so you can assume vertical shear load Sy, so that the horizontal shear load you can substitute it as 0, and with this the formula reduces to minus Sy by Ixx summation BR YR plus integral 0 to S T Y ds. So that you have to consider. So this is how the formula modifies according to the given data, that is skin is fully effective in carrying both shear and direct stress. And plus, since this is a closed section, then you have to add QS naught as well. Okay, so this is a complete formula for this one. So the x-axis is an axis of symmetry, so that Ixy equal to 0, and also the shear center lies on this axis, and apply an arbitrary shear load Sy through S. The internal shear flow distribution is then given by the equation in which Sx equal to 0, Ixy equal to 0. So this is what the equation we consider, minus Sy by x integral 0 to S Td into Y into ds plus summation R equals to 1 to N BR YR plus QS naught you have to add. This is since this is a closed section, and let us assume this as equation number 1. So to proceed in this problem, first let's try to calculate the moment of inertia Ixx for the problem. So the moment of inertia Ixx for the problem, first let's try to write, even since he mentioned that skin is effective in taking all the both direct as well as shear stress, even the moment of inertia calculation also changes. So first you have to calculate the moment of inertia according to the booms, that is the formula summation BR YR square. First BR YR square plus again you have to use the formula for Ixx for the panel, that is BD cube by 12 into area into Y bar square. So that also you have to use, and then you have to write the combined equation for calculating the moment of inertia. So if you try to write this area, and he has given boom area as 100 mm square. So 100 is the boom area, and its corresponding y distance from centroid is nothing but half of the distance, that is 40 mm. So BR YR square, 100 into 40 square, like that you get all are symmetrical, all are same areas and same respective y distances. So therefore you can write 4 times 100 into 40 square. So that is the first thing. 4 times 100 into 40 square, that you have to write. So this is because of the boom areas, booms, moment of inertia due to booms. And next you have to write along with the panel. Okay, so let's try to write for the horizontal panel first. So that is this one. Okay, and so the width is nothing but 0.64 into depth, sorry, width is nothing but 240. Let's try to write for 1 2. I am writing here for 1 2. So width is nothing but 240, and depth BD cube by 12, depth is nothing but 0.64 whole cube by 12, plus I have to write 240 into 0.64 is the area, into its y distance from here to here, it is nothing but 40 square. So that I have to write here. Okay, but here because of the thin wall approximations, 0.64 thickness cube can be made it as 0. So you left with 240 into 0.64 into 40 square, and which you will written here. Okay, next try to, and even for 3 4 also you are going to get the same. So you can multiply this by 2. Okay, so that is given already here, multiply by 2. Okay, next if you look at into the next one, 2 3 as well as 1 4. So 2 3 thickness is different, that is 0.36. 1 4 thickness is given different, that is 0.64. You have to understand. So usually we assume that these are the same thicknesses, but for this problem he has given different thicknesses for 2 3 as well as 4 1. Though they are both vertical webs, though their depth is also same, that is 80 mm, but the thicknesses are different. So you have to consider them separately. So next, for if you try to write for this one 2 3. So BD cube by 12. So B width is nothing but 0.36 into D cube by 12. So D cube depth is nothing but for this one 80 cube by 12 into 0.36 into 80, we write area into y distance. So its centroid for this is nothing but here, the total figure centroid also somewhere here. So it coincides. So therefore the distance is 0. Okay, and similarly for the panel 4 1, 0.64 into 80 cube by 12, even the second term goes to 0 because its centroidal y bar becomes 0 because coincides with the centroidal horizontal axis. So you left with only this one and this one, so that you have to add here as well as here. Okay, and if you try to calculate that, you are going to get moment of inertia as 1.17 into 10 to the power of 6 mm power 4. So only for this kind of problems, when he mentioned that the skin is effective in carrying both direct as well as shear stresses, instead of skin usually takes only the shear, but here he mentioned even it takes the direct stress also. So the calculation of moment of inertia also changes, that you have to take with respect to the booms, and then you have to consider the panels also. Okay, that is the skin between the booms. Similarly, the shear flow formula also you have to consider them separately, right? So now, since this is an open section, what I am trying to do here it is, I am going to cut the section at this point O and then making it as open, and so that I can calculate the open section shear flows O to 1, 1 to 2, 2 to 3, and 3 to 4, and 4, like that. Okay, so first I am cutting the section, and then from the first two terms of the right hand equation, first two terms of the equation 1, so this one term and that's so when you cut the equation, first for the first thing you can consider it as 0, and then QS becomes QBO1 minus SY by IXX integral 0 to S1. So what you can do here it is, and when you try to cut this section, 0 to 1 panel is left. So it's very important to understand here. 0, 1. So you are cutting that and you are calculating this one. So 0, starting from 0, it is plane section. At 0, you don't have any booms. Okay, so only you need to consider only this one. Okay, the first term you need to consider, and for that what I am trying to do here, it is I am taking a section S1 as a section. So when I take this section and I need to consider only Y. Okay, so the total depth from here to here, it is 40 mm, half of this distance, and the distance from 1 to the section is nothing but 40 minus S1, which is nothing but Y. So for Y you have to substitute 40 minus S1 over here, and thickness for this wall is nothing but 0.64. You have to substitute 0.64 into, in place of Y you have to substitute 40 minus S1. So if you try to write this one, so since you consider the section here S1 and you have to take that Y distance not from the point 1, you have to take it from the horizontal axis. So from the axis, if you consider, Y is nothing but plus S1. Okay, so in place of Y you have to consider S1 instead of 40 minus S1. Usually the 40 minus S1 is nothing but the distance from the boom 1, but we don't want the distance from boom 1. In fact, we want from origin O. So therefore that you can consider it as S1. So substituting here thickness as 0.64 and S1 into ds1, and SY you can substitute, and then SY is same as SI, SY, and IXX you got the value, that is nothing but 1.17 into 10 to the power of 6 mm per 4. You can substitute here, and the formula reduces to QB01 equals to minus 0.67 into 10 to the power of minus 6 SY into S1 square. So you can consider this as equation number 2. Okay, now let's moving on for this one, because once you get QB01, and anyway the starting shear flow would be 0, that at O you can substitute S1 equal to 0. So when you substitute S1 equal to 0, you will get Q0, that is the starting shear flow is 0. Anyway we made a cut and made it as open, so therefore obviously the shear flow at the open section will be 0. Now at 1, if you try to calculate, and at 1 means you have to substitute the distance of 40, from here to here it is 40 mm. So you can substitute 40, and so that you are going to get Q1 equals to, and here in place of S1 you have to substitute 40 square, and if you try to multiply with this one, you are going to get Q1 as minus 4.32 into 10 to the power of minus 4 SY. Okay, so this is QB1. So that part is over. Now let's try to write for 1, 2. Okay, so for 1, 2, if you try to write, okay, and 1, 2, at 1 you have the boom, and then panel is also there. So therefore this complete formula you have to consider now. Okay, so for writing QB12 minus SY by IXX integral 0 to S2, and the distribution also I considered from here to here it is S2, so that I have to calculate the distance from the centroidal axis. So from here to up to the section, what is the distance? So it is a constant distance, that is nothing but 40 mm. Okay, so that Y you have to consider it as 40 mm, right? And the thickness for this wall 1, 2 is also again 0.64. So when you try to substitute in the formula, thickness is 0.64, and Y you have to substitute 40 into ds2 plus what you have to write, BR into YR corresponding to boom 1. So boom 1, the area is nothing but 100 mm square is the boom area, and 40 mm is the distance for boom 1 from here to here. So that you have to add, and after that QS0. Now in this case for 1, 2, the starting shear flow would be 0, 1. So that you have to substitute. Okay, so the starting shear flow is nothing but QB1. So that you can substitute here. So QB1, that is equals to minus 4.32 into 10 to the power of minus 4 SY, that you have to substitute. So once you get this one, so you can integrate this between 0 to S2. So you get the QB12 distribution as minus 10 to the power of minus 4 into SY into 0.22 S2 plus 38.52, that you are going to get QB12. So this you can consider as equation number 3. Okay, and again here you can substitute the boundary conditions, and at 1 you can substitute S2 equal to 0, S2 equal to 0, and then you left with the previous equation what you got here. And at 2 you can substitute S2 equals to, what is the distance you have from here to here? It is 240. So at 2 you can substitute S2 equals to 240 mm. Substitute in this equation, you are going to get QB2. Once you get this one, QB2, this QB1, which is same as this one. Okay. So when you substitute S2 equal to 240 mm, you are going to get QB2, and substitute here in this equation, you are going to get QB2, that is equals to minus 91.32 into 10 to the power of minus 4 SY. Okay. And similarly, the next shear flow would be 2-3, and for 2-3 also you can consider like this, and minus SY by IXX, and for distribution you can consider this as S3, and therefore the distance from here to here is nothing but 40 minus S3, that is Y you have to consider from here to here. So total depth is 40 mm, and then subtract this S3, you are going to get from the centroidal axis Y is nothing but 40 minus S3. So you can substitute that. Thickness of this 2-3 is 0.36, and 40 minus S3 is the Y distance into DS3 plus boom area of 2 and its respective Y distance. So that you have to add, that is 100 is the area and 40 is the Y distance, and for which you need to add 1-2. For 2-3 the starting shear flow would be 1-2. So you have to add 1-2 this equation. So for 1-2 or QB2 you have to add. The starting shear flow would be QB2 for 2-3. So that QB2 you have to add here, that is minus 91.32 into 10 to the power of minus 4 SY. And if you integrate this and let's try to write the equation, you are going to get QB23, that is equals to minus 10 to the power of minus 4 into SY of 0.12 S3 minus 0.15 into 10 to the power of minus 2 S3 square plus 125.52. So this you can consider as equation number 4. Okay. So once you get QB23 like this, now you can the remaining shear flow distribution follows from symmetry, and you need to calculate the QS0 because you made a cut here and you assumed the starting shear flow is 0, so that you have to calculate first QS0, and the formula for QS0 is nothing but equals to minus of cyclic integral of QB by T into ds divided by cyclic integral of ds by T. Now let's try to find out for this one cyclic integral of ds by T. So cyclic integral of ds by T is nothing but, ds is nothing but the length of the panel divided by its respective thickness. So if you try to write this one from this diagram, so for 1-2 the length would be 240. So 240 divided by 0.64 plus this one is 80 divided by 0.36 plus 240 divided by 0.64 plus 80 divided by 0.64. So that will be the cyclic integral of ds by T. So that you can calculate here, which you get it as 1097.2. Okay. And when you try to substitute in this equation, when you substitute all, that is QB01 and QB12, QB23 from equations 2 to 4, and then you can write this as QS0 equals to what you can write here, it is 1097.2. you can write it as it is, and then you have to substitute QB01. For example, what is QB01 from equation 2? QB01 is nothing but minus 0.27 into 10 to the power of minus 6 SY into S1 square. Okay, so that you have to write, and SY you can take common, and even 2 into 10 to the power of minus 4 also you can take common. And when you try to write this for 01, the limits are 0 to 40 into and 0.27 into 10 to the power of minus 2 divided by 0.64 into S1 square ds1. So you can write that QB01 you can write as it is, plus the second one is nothing but you can write for the other one, panel 1 to 2, that is 0 to 240 and 1 by 0.4, and you can write that equation number 3, that is 0.22 S2 plus 38.52 into ds2 plus again 0 to 40 for the third one, and you can write 1 divided by 0. That means what you can do here it is you can write the equation for the half of the section. Okay, so 0 to 1, 1 to 2, and 2 to this O0 you can consider, right? So that the rest of the beam shear flow would be same because of symmetry on the lower half of the section. So 0, 1, 1, 2 and 2 O0. So for 0, 1 the limits are from 0 to 40, and for 1, 2 the limits are from 0 to 240, and for 2 O dash again the limits are from 0 to 40. Okay, so that you have to, we are writing here. So 0 to 40 for the first one, 0 to 240 for the second one, and 0 to 40 for the third one, divided by 1 divided by its thickness, and trying to write that equation number 4, that is nothing but 0.12 S3 minus 0.15 into 10 to the power of minus 2 S3 square plus 125.52 into DS3. Okay, so when you integrate properly with the and substitute the respective limits, separate limits for this one and third one, and then you are going to get the QS0 is equals to 70.3 into 10 to the power of minus 4 into SY. So once you get this QS0, you have to superimpose onto the section to get the actual shear flows. So now what we have got here is QB not 01 you got, that is minus 0.27 into 10 to the power of minus 6 SY into S1 square. And then what we are going to write here it is, so this we have to add. So QB, so Q01 that is equals to, here we got 70.3 10 to the power of minus 4. So that 70.3 into 10 to the power of minus 4 we have to add to this QB01. So how much we got QB01? We got it as minus 0.27 into 10 to the power of minus 6 into SY into S1 square. For that you have to add. So 0.27 into 10 to the power of minus 2 S1 square. For that I am adding what we got the shear flow, that is 70.3 that we are adding. Okay, and when you take common you get minus this one, so this will be what, Q01. And similarly Q12, Q34 also you can get by adding its 70.3, and Q23 also you are going to get. Once you get the actual shear flows 1, 2, 2, 3 and Q01, you can take the moment about the midpoints of the wall 2, 3. So you have to take the moment about midpoint, that is about O dash. Okay, so when you try to take moment about O dash, and this shear flow as it is passing through the same point, so that does not give any moment. So the only moment what you get is, you get moment due to 0, 1, you get moment due to 1, 2, and that you can completely multiply by 2 even you get for the lower sections. Okay, so this is the moment equation. The 2 is written outside of the bracket sign, and then you can write for the 3 equations, that is 0 to 40, 0 to 240 and then 0 to 40 equation also you can write, and you can substitute the moment due to shear flow, that is equals to moment due to shear load. And when you try to solve this equation you are going to get here, so the left side would be moment due to the shear load and the right side would be moment due to shear flow. So as I mentioned, 0 to 40 is nothing but that 0, 1 you can consider the moment, and this is 1 to 2. Okay, and then completely you have to multiply by 2 so that you can get the shear center. So SY into zeta S is the moment due to the shear load, SY into zeta S, it gives anti-clockwise moment, and for even 0, 1 you get anti-clockwise, 1 to 2 also you get anti-clockwise. So equating the moment due to the shear load SY into zeta X to the moment due to shear load, moment due to shear flow. Okay, and since both all are anti-clockwise, you can consider this is anti-clockwise, these are anti-clockwise, and then you can write for 0, 1 moment. So the moment for this 0, 1 is nothing but you can consider in terms of integrals because you got distributions. So perpendicular distance for 0, 1 is from here to here, it is 240 mm, and for 1, 2 the perpendicular distance from here to here is nothing but half of the distance, that is 40. So that you can consider, and you can substitute here by considering the equations 0 to 40, that is 240 is the perpendicular distance for the first one and 40 is the perpendicular distance for the second one, and rest of thing you are writing as it is, the shear flow, that is this is Q01 and this is Q12, you are writing from here and here, and then multiplying by DS1, DS2, and also writing the limits 0 to 40, 0 to 240. So this equation, when you try to integrate between the limits, and SY cancel outs on both sides, and you get horizontal position of shear center zeta s, that is equals to minus 142.5 mm. So you need to solve this one. For example, for this one, s1 square is there. Okay, when you integrate this, it becomes s1 cube by 3, and you have to substitute the limits 0 to 40 in this. Okay, and here you got and here 70.3 is there, so 70.3 becomes 70.3 s1, and here s2 becomes s2 square by 2, and here you get s2, this is s1 square becomes cube by 3. Okay, so after that you can substitute the limits 0 to 40 in this equation, and in this one you can substitute 0 to 240, and you can reduce the calculations, and you get zeta s equals to 142.5 mm. So this is how we try to calculate the position of shear center and shear flow distribution for this problem, in which he clearly mentioned that skin is fully effective in bending as well as shear. Now, if for this problem, if he mentioned that the booms carry only direct stresses, but the skin is effective in taking the shear instead of this, if this is not given, then here you don't get this integral, and here you don't get this integral, here you don't get from here to here, you don't get this, and the calculation reduces. That is a usual practice. Almost all the questions are like that, but only this question is different, so that we have to follow the procedure like this. Okay, so that's it from today's session. So let's try to meet in some more problems in the next session. Okay, so thank you everyone for watching.